Picture this, an environment so intense, so extreme, that your standard everyday metals would literally just warp, weaken, and completely fail under the stress. I mean, we're talking about temperatures hitting a scorching 650 degrees Celsius inside ultra-supercritical boilers in petrochemical plants. Just to put that into perspective, that is easily hot enough to melt lead or aluminum into a puddle. So it begs the question, what kind of tubing can possibly withstand that kind of hellish environment without just rupturing? Well, welcome to this explainer. Today, we're tackling a really major, foundational question for industrial engineering. What exactly is ASTM A213? We're going to decode this standard, which honestly serves as the critical artery of modern power generation and heavy industry. If your work touches high-pressure heat transfer in any way, understanding this standard isn't just a nice-to-have kind of thing, it's absolutely vital. Okay, let's dive right in. Here's a quick roadmap of what we're covering today. We'll start off by defining ASTM A213, then we'll break down the key grades and their properties. After that, we'll look at the strict manufacturing and testing rules, and finally, we'll compare it against ASTM A335 and ASTM A269 so you know exactly when to specify this material. All right, kicking things off with Section 1, defining ASTM A213. And it's important to realize right out of the gate that we aren't talking about off-the-shelf plumbing here. These are highly engineered survival conduits. By its formal definition, and you might also know this by its ASME equivalent, SA213, this is the standard specification for seamless ferritic and austenitic alloy steel boiler, superheater, and heat exchanger tubes. Now, the absolute keywords you need to lock onto here are seamless and high temperature. There is no welding happening here. These are continuous, solid pieces of metal engineered specifically for intense, high-pressure service. And looking at the scope, the size range is actually pretty wild. It goes from a tiny nominal pipe size of 1/4 inch all the way up to a massive 24 inches. Plus, they feature incredibly heavy weld thicknesses. We're talking schedules 40 through 160. And why does that matter? Because these things are deployed right in the absolute belly of boilers, superheaters, and heat exchangers. Their one job is to safely contain and transfer energy that would otherwise be a literal bomb if the material gave out. Moving right along to Section 2, key grades and properties. Let's peek under the hood, because the real magic of A213 is all about its highly specific chemical metallurgy. Now, what's really interesting here is the clear evolution of capability. Think about it like a ladder. If you're running a standard boiler up to, say, 580 degrees Celsius, ferritic alloys like T11 or T22 are your cost-effective, everyday workhorses. But as modern plants push for crazy high thermal efficiency, we have to climb that ladder. Grade T91 jumps up to 625 degrees with amazing creep strength. And for those absolute peak ultra-supercritical applications, that's where we step into the austenitic stainless steels like TP347H, which easily handles 650 degrees and beyond. So how exactly do they achieve this kind of resilience? Well, it's a bit like baking, right? But a highly volatile cake. It is all in the recipe. Take a look at a T-series grade like T22 versus a TP series like TP316L. The chromium gives you oxidation resistance, and molybdenum brings that crucial high-temp strength. But check out the nickel component. The T22 doesn't have any, but the austenitic TP series dumps in a ton of nickel, up to 14%, and massively boosts the chromium. That specific tweak is what unlocks next-level corrosion and heat resistance for the absolute worst environments. And all that highly specific chemistry, it translates directly into massive mechanical performance. Take grade T91, for example. It has a minimum yield point of 415 megapascals. These strict baselines mean that when thermal expansion kicks in, or when internal pressure spikes, the tube holds its shape, period. Honestly, if you take away nothing else from this explainer today, remember this. A213's chemistry is mathematically formulated to prevent rupture. But of course, a great chemical recipe means nothing if you don't bake it right, right? That brings us to Section 3, manufacturing and strict testing. Listen, the ASTM A213 standard leaves absolutely zero room for interpretation. The manufacturing process must be seamless. That means hot rolling or cold drawing solid steel billets. Again, no welding allowed.
Plus, they mandate highly specific heat treatments, like full or isothermal annealing, just to make sure the metal's internal microstructure is completely aligned and stress-free before it ever gets loaded onto a truck.
And this brilliantly illustrates the kind of insane precision we're dealing with. For an outside diameter of under an inch, so 25.4 millimeters, a cold-drawn A213 tube is held to a tolerance of plus or minus 0.10 millimeters. To put that in perspective, that is roughly the thickness of a single strand of human hair. It's a level of exactness that guarantees a perfect fit and perfect flow inside complex heat exchangers. To guarantee those tolerances, the testing gauntlet they run these through is, well, it's brutal. Every single tube goes through a mandatory hydrostatic test or a super strict non-destructive equivalent like eddy current testing. But they don't stop there. They pull samples from every single heat treatment lot to literally rip them apart in tensile tests. They flatten them, they flare them to check ductility, they test the hardness. For austenitic grades, they even get out the microscopes to measure the grain size. This obsessive quality control is exactly why the standard is the holy grail for power generation. So you're probably asking yourself, with so many standards out there, when do I actually specify A213 over something similar? Let's clear that up in Section 4 by comparing it to a very common counterpart, ASTM A335. Here is the crucial takeaway. It's all about understanding the difference between a tube and a pipe in this specific context. A213 is designed for smaller diameter tubes. These act as the actual heat transfer surfaces right inside the boiler. A335, on the other hand, is for the larger diameter pipes that carry that superheated steam away to the rest of the plant. Think of it like this. A213 is the heat exchanger itself, and A335 is the transport plumbing. All right, that brings us to our final comparison in Section 5. What happens when we put A213 up against a general service standard like ASTM A269? Because they both cover seamless stainless steel tubing, the line can feel a little blurry. Let's see how this builds, because when you compare the two, you immediately spot a massive engineering safety factor: wall thickness. A269 allows for an average wall thickness, meaning it can safely fluctuate up or down by 10%. But A213, it mandates a minimum wall thickness. If you order a 1 millimeter wall A213 tube, it is legally not allowed to be thinner than 1 millimeter at any single point. Plus, A269 allows for welded tubes and makes that hydrostatic test optional. A213 is strictly seamless, and testing is 100% mandatory. Look, because of these insanely strict manufacturing rules, the mandatory destructive testing, and that minimum wall thickness guarantee, yeah, ASTM A213 is definitely going to cost you more upfront than a general service standard, but honestly, it's a completely necessary investment. You aren't just paying for a piece of steel here. You are paying for unmatched high-pressure reliability. You're buying the peace of mind that your tube won't catastrophically explode inside a 600-degree boiler. So that leaves us with one final thought for your own work. The next time you're designing a heat transfer system or maybe evaluating an industrial upgrade, you really have to ask yourself, will this project require minimum wall, high-temp reliability? Because if the environment is extreme, if the pressure is intense, and if failure is simply not an option, well, you now know exactly why ASTM A213 is the only standard you should be calling out. Thanks so much for joining me on this explainer, and hey, keep engineering safe out there.